instead of asking the D query, I'll compare it to the D query. We ask for the degree of each node. We actually don't care about the association between people and their degrees. We just want a multiset of the degrees that occur in the graph. So any permutation of those numbers is fine to return to us as an analyst. In fact, the permutation that we'll choose is the permutation which ranks the degrees. So I start with the lowest degree in the list and I go up to the highest degree. I'm going to add random noise to that query, but I'm going to ask for the query in ranked order. It turns out, and you have to think about this a little bit, and I won't prove it to you, but it's not too hard to see that the sensitivity, even if you sort the list, doesn't change. It's still the same sensitivity, which means the same noise will be added. But the advantage of asking for this ranked query is that I have a whole set of constraints that I know hold over the true answer. And when they're violated by my noisy output that I get, I can use that to my benefit. So let me show you how we use that. This is a toy example, and I'm displaying the degree sequence a little bit differently here. This example has a bunch of 10-degree nodes, and then a 14-degree node, and then a few 18-degree nodes. And they're displayed horizontally there by in order and the degree on the y-axis. That's the true sequence is in black circles. The random output I get is going to add independent noise to each of those degrees. So instead of getting 10 across all those first degrees, I'm going to get the green dots, which are slightly higher than 10, slightly lower than 10. And then I'm going to get some other values. So this is a little strange because it violates the sort constraint. A sorted list is non-decreasing. It can be flat, but it can't go down, right? So what's strange about this is that the 19th element in my array should be the 19th smallest degree, but some noise has been added, and now it actually looks like the smallest degree. And I know that can't be right. So as an analyst, I can refine the green sequence and come up with a better estimate. The way we do that, there's more than one way to do that. The way we do that is we generate an inferred sequence, this red line, which minimizes, it's a non-decreasing sequence, so it satisfies that sort constraint. And it's the non-decreasing sequence that minimizes the distance between the observed values. You could minimize the L1 distance, but we happen to minimize the L2 distance because it gives us a unique answer, whereas the L1 distance doesn't. So, we take the noisy output that we get. We know that some constraints are supposed to hold. Those constraints are violated. So we refine the noisy output and we get a better estimate. That's the basic idea here. Here's what it looks like when we run experiments on, here it's some synthetic data. So the black dotted line is the true degree sequence, and the red line is, the green line is what we would have gotten with the standard technique. The red line, which is pretty close to the black line, is what we get from the inferred sequence. So it's a lot better, and the two cases here have different privacy settings, so there's more noise added in the case above. This, on the right, that's the same example data, and on the left are two new data sets, ORCID and LiveJournal. You can see that the red series is quite close. So what's going on here? It seems, when you first hear about this, like I've given you the noisy output that you told me I had to add this much noise to make it private. But then I've somehow inferred a better answer. So haven't I weakened the privacy? Is this a threat to the privacy guarantee? And it's not. So what I've done is I've formulated my query in a way that has constraints that hold. The constraints are a property of the query, though. They say nothing about the data. I submit the query to the differentially private interface, and I follow all the rules that were laid out for me by the differentially private mechanism. In fact, we kind of use differential privacy in only the standard way. All of our techniques are sort of post-processing the output. So we get the noisy output, which I'm writing here as S tilde, and then we perform our inference technique using no information from the database to infer S bar, which is the better sequence. So this is my argument for why it doesn't weaken privacy. The intuition is that the standard independent Laplace noise that we add using the construction that's classical for differential privacy adds more noise than is necessary. It's certainly sufficient for differential privacy, but no one has shown that it's necessary for differential privacy. And what these results show is that it's not necessary. It's more noise than we need. So by using inference, we're in some sense adding noise where the noise needs to be. The sorting trick, in some subtle way, capitalizes on the fact that the sorted sequence I'm asking for can only change in certain parts. So if I add an edge to a graph, remember that I change 2 degrees each by 1. But in the sorted list, if there's a bunch of 10-degree nodes, I can never change the fact that the 10th node in that list is 10. I could change the ones at the tail of that common sequence and at the end, and I could change these other ones, but I can't change those ones in the middle, so I can get away with adding less noise there. That's the intuition. I mean, making that, realizing that is tricky, because if you add a different noise distribution, you have to still prove that the differential privacy holds. So we tried to represent the noise that we add to the inferred sequence can be seen as some random sequence produced from the original input, but it seems very difficult to describe that probability distribution directly, and our inference step kind of gets around that. If you look empirically at how we add noise by running a bunch of experiments on a sequence like this, you'll see that the noise that we add, what we do is we run a bunch of experiments where we add the noise and then do the inference and get the better answer out, and then we look at how noisy that better answer is. And what it reflects is that noise is added where the sequence can change and not otherwise. Okay, so the theoretical bits are that we can also prove that our error is lower. So instead of having order n error for the S tilde sequence, we have error that's polylogarithmic in n, which is good, and there's a factor d, which is determined exactly by what I was saying, the length of sequences of common degree. The longer those sequences of common degree, the better the trick works, the sorting trick works, and error is reduced. The thing that's great about degree sequences of social networks is they have lots of common degrees, especially in the earlier regions. So in practice, we get a big boost from this technique. The algorithm's also efficient, so finding that red line, minimizing the L2 distance, is a little tricky. I mean, it's worth asking whether you can do that efficiently. You can't always apply such constraints efficiently, but in this case we can. And we've got that running in recent work in linear time in the sequence. So we could actually run this algorithm on massive graphs. Okay, I'm getting close to running out of time, so I'm going to skip the 2 slides I have on privately counting motifs. The main idea here, motif analysis is basically studying the frequency of occurrence of small patterns in a social network. So a classic example is transitivity. How often if I'm friends with A and I'm friends with B, are A and B friends, and how likely does that occur? But in general, you might want to study other patterns that you think are interesting, or you might want to search for patterns that occur more often than you expect them to occur, things like that. Counting motifs is a fundamentally harder analysis to do under differential privacy. It's higher sensitivity. In fact, its sensitivity is very high, so much so that standard differential techniques are probably going to return useless answers. So we have a technique which weakened the privacy notion a little bit and improves the error. So I'm going to skip over this and talk briefly about where we're headed with this work. So I mentioned in the beginning that data publication is great for ease of use because you can hand somebody a graph and they can study it. We're using output perturbation, so we're considering specific tasks, breaking them into a bunch of queries, and learning if we can answer those queries accurately. So I think that's the first step in a process which we hope will result in techniques for data publishing. So I'd like to still hand the analyst